Hi, I'm Mr. Ramage, and this video lesson will serve as an introduction to the scientific revolution. So in our study of the Enlightenment period, we have to kind of go back and see what science is like in the 1500s. Well, what science was like in the 1500s was actually what science was like back in the ancient times of the Greeks and the Romans, where philosophers like Socrates and Aristotle determined how the world worked, basically through observation alone. Ancient science was not exactly the type of science we have today. The scientific method didn't really exist, and most of what people believed to be true about the world was not really true at all. Science was more like philosophy than it was actual science. Simple observations and empiricism is just not going to be enough. But the fact is, for hundreds and hundreds of years, what people in Europe especially knew of the world came from these ancient philosophers. Things are going to begin to change a lot during the period of the Renaissance. As ancient information is rediscovered, people begin to understand that there were disagreements amongst these ancient philosophers. Specifically, people like Plato and Archimedes had other ideas about how the world worked and how things functioned. So we begin to question what we really do know about the world around us. Could the ancients have been wrong? Do we really truly understand how things work? During the Renaissance, there was also a resurgence of math as more and more higher level math was required in terms of increased trade and the sale of goods, more contact with other cultures from the Middle East and Asia. We are using more math to build bigger and better ships, to measure the amount of cargo that can be carried in those ships, to improve our building techniques and map-making skills. There was also a big movement to reform the calendar to make it more accurate. So math was very much being applied to trying to figure out everything. And math was sort of the key to understanding the universe and understanding how things work. So we're becoming much more mathematically focused, and that is going to lead to more questions, but also finding proof, finding evidence of how things work and why they work. Speaking of the universe, what do we actually know about our place in the universe? Well, we're going back to ancient philosophers like Ptolemy and Aristotle, whose observations of the heavens place us in what's known as a geocentric universe. And that means that the Earth is at the center of this universe. The Earth is at the center and it's stationary. It does not move, it does not spin, it does not tilt on its axis, but rather sits still in the very center of the entire universe, and everything else revolves around it in perfect circles. The known planets of the time, the moon, the sun, the stars, all orbit the Earth in perfect circles, and this is what people believe to be true. And this geocentric theory of the universe is highly supported by the Catholic Church because it fits their sort of creation story, right? The Earth is at the center. Where else would God put it? It's surrounded by stars, and beyond the stars are the heavens, and that's where God is, and that's where you'll go after you die, as long as you live a good life. So a geocentric universe falls in line with Catholic dogma. It sounds great, it's perfect, and if you question or contradict the information of a geocentric universe, the church would label you to be a heretic. So going against this accepted belief could get you into trouble, as we'll learn later on in our unit of study when we talk about Galileo. So this also again fits into the way people did science back then. If Spider-Man were to go outside and stand still all day long, he wouldn't feel himself moving, but he would actually see and observe the sun moving. He wouldn't feel the earth beneath his feet moving at all. He did not change position. He simply observed the sun rising in the east and setting in the west. So common sense would tell you that, yes, it is the sun that's moving around the earth, not the earth moving around the sun. So again, if you were to propose a different idea, you're kind of challenging people's everyday experience of what they see and what they feel. Well, the reality is the Earth is moving quite a bit. It's spinning on its axis at about 1,000 miles per hour and also traveling around the sun at about 67,000 miles per hour. That's about 18.5 miles per second. So yeah, the Earth is doing quite a bit of movement. So what begins to change? How does this view of the universe shift away from a church-supported geocentric universe, one that was proposed by ancient philosophers, and how do we get to the point where we begin to really understand how our universe is structured? Well, that all begins with Nicholas Copernicus, and we're not going to do a deep dive on him, but he was a mathematician, a physician, an astronomer from Poland, super smart guy, and between 1508 and 1514, he begins to develop his heliocentric theory of the universe, that based on his observations and based on his math, the universe is not centered around the Earth, but in fact centered around the sun. And this is the heliocentric theory of the universe that is put out there by Copernicus. Copernicus is going to also correctly identify the order of the 6 planets as they orbit around the sun and describes their orbits with some accuracy. Now, he did still believe that they moved in perfect circles, but he was sort of conflicted. The evidence that he gathered in his math showed that moving in circles was maybe not what they were doing, but he didn't really have anything to prove otherwise. Now, he also placed the sun at the center of the entire universe, and we know that that's not true, but he does identify the sun as the center and this body that all the other planets, including the Earth, are going to orbit around. So Copernicus gets a lot right based on simple math and observations. Now, back in Ptolemy's time, and all sorts of other astronomers and astrologists had to come up with very clever ways to try to explain the motions of the planets. Having them move in circles just didn't work, and to explain why they moved in circles, they had to come up with epicycles, which is basically a planet doing a circle while it orbits the Earth. So this is where Copernicus kind of gets stuck, but he decides to stick with these epicycles. Now, he also identified that the Earth rotates on its axis each day, that axis being 23.4 degrees, and that one rotation around the sun equaled a calendar year. So again, Copernicus, through simple observation and some pretty complex math, is able to come up with some pretty accurate information. In 1534, basically on his deathbed, he published his book on the revolutions of the heavenly spheres. Possibly because he was afraid that there would be backlash against him. He was maybe afraid of what people would say or the church would do with these heretical ideas, but his book's published right before he dies. And one of the problems with his book is that it was written for mathematicians. It is extraordinarily difficult to read and understand and comprehend unless you can understand this very, very high level of math. So because the book's not really accessible, few people are going to read it, and many people are going to simply dismiss his theories. It's all based on math, and math could be faked. So there's no real observations, there's no real evidence other than the math. So because of that, his book kind of goes unnoticed. But people do read his book. One of those being Johann Kepler, a German mathematician who was extremely interested in Copernicus's work and wanted to find the evidence to support this claim of a sun-centered universe. Kepler is going to find himself working alongside a very famous astronomer named Tycho Brahe, who was obsessed with studying Mars's unique orbit. Because, remember, with these epicycles, we've got the planets doing circular motions around the Earth, and Mars at times appeared to be going backwards. When Brahe died in 1601, Kepler gets his hands on his research, which Brahe kind of kept from him, and Kepler dives in and discovers the reason that Mars appears to be going backwards is that it's not orbiting the sun in a circular orbit, it's orbiting an elliptical orbit. So now we have the correct information to understand the movement of the planet Mars and how it relates to Earth and the Sun, that it's not circular at all, and these epicycles are not necessary anymore, but rather moves in an elliptical orbit around the Sun. This leads Kepler to the development of his three laws that, number one, planets moved in elliptical orbits, 2, planets moved faster depending on their distance to the sun, and 3, the length of a planet's orbit around the sun is influenced by its distance from the sun. And down at the bottom of the screen are some of the works that he produces that include that information. So, this is really the start of this scientific revolution as we begin to use mathematics and begin to develop evidence to prove how things work. So, some key takeaways from this lesson would be that most of what was known about the world in the 1500s came from ancient philosophers and the use of empiricism, and it just wasn't good enough anymore. The world is a very complex place, and we need some science to better understand how it works. Advancements in mathematics would help the scientific revolution begin as math became a cornerstone of how people understood how things worked. Ancient philosophers and the church supported the accepted geocentric theory of the universe, and anyone that challenged it was thought to be a heretic. Copernicus was the first European astronomer to publish data supporting a heliocentric universe, and Tycho Brahe and Johann Kepler built upon the work of Copernicus and were able to support some of his theories with evidence. I hope you enjoyed this video lesson on the introduction to the scientific revolution, and I hope you learned something. Thanks for watching.